And we're here at last. This is part 5, the last installment in the networking series. There's just a few specific implementation details that I want to run past you so you're familiar with the general concepts. Alas, we don't have time in class to implement all of this in-game. If you want some networking experience, let me suggest Sanjay's Unreal class, Advanced Gameplay Programming is what he's calling that. It's available in the falls, plug for that. That is taught in Unreal, and the whole second half of the class involves multiplayer networked code. So that's the best way here at school, I think, to get real hands-on networking experience. Okay, so with that in mind, let's jump into these last few details. I'm reminded of a story, something that happened a few years back in one of our AGP classes. We had a group that was working on a multiplayer game, and they started with multiplayer, split screen, but they really wanted to go to a networked multiplayer model. And they started off with, of course, their single player architecture, and they were trying to adapt it into a multiplayer mode. And what they ended up doing was splitting their code and splitting their team into two separate teams. One team would continue working on the single player version of the game, and the other team was going to be making the network version of the game. The idea, of course, is that like many games that are multiplayer, they have a single player campaign as part of the package. It sort of serves as a tutorial, and it gives backstory, and it serves a whole nother player base that really enjoys that single player kind of style. While then the idea is that then you could use the same, engine and the whole same code for your multiplayer, player versus player game. And that's what they were trying to do exactly. Unfortunately, it went on for quite a while before I realized that's what they had done. And I wish I had this moment that I'm having right now to tell you what I wanted to tell them, which is don't write two separate versions of all of that code, all the player controls, all the character motion, all of that stuff. You have to write one for single player and one for multiplayer. That's a lot of work. It's really daunting. And then trying to get them to both be the same somehow is going to be just a total pain. Lucky for us, John Carmack worked this out decades ago. The secret is to just make the multiplayer game. You make that first, and you have a client-server architecture, and you use the trick where we say one of the players in the session is the server. So that player has a client and has controls and a player avatar and everything, but they're also serving as the server. And what have you got now? Well, now you've got your single player mode built right in to the system. So you don't have to write everything twice. The way it works is that right there on your client, you enter the commands, you enter the machines, you hit the jump button. The jump button is sent to the server. You send the command to the server. And what is that? Well, the server is just localhost. So it sends that command right back to yourself. And it doesn't go anywhere, it just goes to yourself. And the server code, which is running right here in your own code base, receives the command and then processes it as if a remote player had given it, using the exact same code. Processes the jump command and then sends back down to all the players in the game that, player 1 jumps. And lo and behold, well, that's you, again, on localhost. So it just sends it right back to yourself. And you can easily rig that up to where you don't even have to you don't send a network packet. You just take the message that you're going to send, put it in the send buffer, and then just pass the send buffer to the server function. The server is just a function that's part of your code now. And so this means that the game plays exactly the same. The code is written once and works really well. When I first heard this whole thing, it sounded really cumbersome and overcomplicated. Why do I have to be a server for a single player game? That's nuts. Well, the reason is because now I can have a multiplayer game. if I want the option of a multiplayer game, I'm going to need that. I'm going to need that client-server handoff at some point. So this opens up that possibility and makes it very flexible. There's a couple other tricks. It's not written on the slide here, but let me just toss at you a couple other tricks you can do with this. One of the things that you'll notice is, of course, the server. When you're in a multiplayer game, the player who's the server has no lag because their commands go straight to themselves with no ping time. And that means that it's not going to be the same for other players who have a lag on everything that they do. Maybe that's unfair. And by the same token, when you're playing the single player campaign, you don't have any lag, but then you jump into a multiplayer session, and now all of these commands that you've learned, and you've got your muscle memory down for exactly when to hit that jump button. And now with the lag, it's not right. So there's a trick you can do to simulate some lag. You can take the commands that are going into that server buffer, right? The commands that you would normally send over to the server over the network, put them into a little buffer, a little FIFO queue of some sort, and delay them by a little bit in the queue. So instead of feeding them directly to the server or sending them over the network, in this I'm both a client and the server mode, you can put them into a little buffer, and after a short delay, then send them through the server code to simulate the amount of lag that would naturally be felt in an internet environment. I mentioned before lockstep peer-to-peer, and I mentioned using it for real-time strategy games, such as this one is StarCraft. First of all, why would we do this? I've seen many people here at school making real-time strategy games just using the Unreal Engine, which is not a lockstep peer-to-peer. It is a client-server UDP system with server authority. So how do they make that work? Well, they just sort of get by. It's not the ideal solution, and the reason for that is because the numbers of units that are moving in these real-time strategy games can be well into the hundreds of units. And sending, good updates for all of those units can be prohibitive. It's much smaller packet of data would be to simply send the commands that the player is issuing over the system. Instead of the update of the position of all 100 of my units, instead send over a selection group, like which units are currently selected, and then a single move to command. So one mouse click is a single move to command for this entire group of units. And that's sort of a very effective data compression technique. And that works well for games like this, real-time strategy. Now, because we're moving in lockstep, there are some obvious downsides. The first one is nobody in the game, no player can advance to the next frame until every single player is ready to advance to the next frame. So if one player has a laggy connection or a slow graphics card, all players in the system have to wait until that player is ready before they can update. Ultimately, the way this works is really like a turn-based system where we each take our turn, like tic-tac-toe. You take as long as you want, make a selection, and then we move to the next person, then they make a selection. And it works just like that, only the turns are fractions of a second long. And if you don't make any selection, we just move on to the next person's turn. That's what makes real time. In practice, the way games like StarCraft would work is that we only send those commands about 10 times per second. We don't send it at every frame. We may update the graphics at 60 frames per second, but the network code can't keep up with that. As we know, that's not enough time for the commands to get through everyone's network connection. So what we'll do is send the commands at a rate of, let's say, 10 times per second. But that leaves, many frames in between that are just graphic updates. So we'll continue running the animations for the characters. We'll move all the characters, but we're not going to run any logical commands at all, except on those special frames where the commands are coming in. So when you're playing the game, all the commands you're clicking, your mouse clicks and you say, hey, you harvester, go get that wood. That command to move that unit goes into a buffer, and it is sent over the network to all the other peers, and they'll all get the commands and stack them into buffers and sort them in the exact same order. And then when it's time, when that 1/10 of a second rolls around, everyone executes their commands. And it's not until then that you actually have the chance to move a unit. So that can be kind of laggy and feels unresponsive. There's another little trick here that I'm pointing out. It takes a while for your command to go through in this system. So we can hide this lag on your own personal client by having your unit make a sound or play a little animation. So, say your little lumberjack unit, go harvest that wood. And what'll happen the instant you mouse click is that little unit will say, yes, sir, and do a little salute. And then it'll start walking, right? While it was doing that salute, the command was just sitting in the buffer. Nothing was happening yet except a little visual flare that happens right on your client that tells, that gives you that instant feedback response. The other players in the system, they won't see that. They won't hear that yes, sir, call, because that's only happening just to give you the feel of instantaneous response while we're waiting for this lockstep to take place. So, speaking of lockstep, there's another category of game that can effectively use this as well, and we can even take it to the next level by introducing something called rollback or re-simulation. So this type of game I'm showing here would be the fighting game genre. Now, it used to be that the concept of a networked fighting game was a pipe dream. Lag in one of these fast Twitch-based fighting games was just unacceptable. So how would we deal with it? Now that machines are faster and networks are faster, we have the opportunity to do something really pretty incredible. So here I have a link to a GDC talk that if you find this at all interesting, I suggest you go through and read. Let me summarize for you. In this case, we would be doing something like a lockstep update where we receive commands from both players and we execute them in order. But what's different here is we do not wait to receive the commands from the other client. We just go ahead and process the commands that we've got for ourselves immediately. And then when you do get commands from the other player, those are lagged. They're now out of date. So what do? We roll back in time. We actually roll the whole simulation back. That's where it's called rollback. We roll back to an earlier time when those commands were supposed to be entered into the queue and insert those commands into the queue. And then we repeat the simulation from that point forward. And that's where the name re-simulation comes from. Let's say I'm going to push the heavy attack, the big slow attack button. I hit that button and I start winding up immediately. The command immediately takes place on my client and simultaneously sends as a command over to the other player. And I start doing the wind up for the big punch. Meanwhile, while that animation is playing, a few frames into that animation, I receive the command from the other player. The other player says they did the quick jab move. Now, that quick jab move is so fast, it should have interrupted my attack. But it's too late now. I'm already into the attack. So what do? I go back 3 frames to the moment when that command should have arrived. So I'll roll back my simulation to where that command goes in the command queue, and insert it into the command queue. And now I roll the simulation forward again. And what we see is that the quick jab from the other player begins, and then my heavy attack begins, and we roll forward now 3 frames to where that quick jab actually punches me in the face. And I now go into my hit reaction because the punch has landed. So by being able to roll back in time, we can maintain a lockstep update without having to wait and do the lag. Instead, we do sort of what we said with the prediction and interpolation model. We're doing a predictive lockstep update. And then when we get the old commands, we execute them after the fact. Hopefully you found that one interesting. That is multiplayer networking in a nutshell. Unfortunately, we don't have time for a lab on this. I would recommend you investigate Sanjay's advanced gameplay programming to get yourself some practice at doing some hands-on with network gameplay. Okay, I'll see you in class.